Hello folks, in this video we are diving into the fascinating world of liquid-liquid extraction, the theoretical side. And we are going to unravel the essential equations which are behind the liquid-liquid extraction. And remember, since liquid-liquid extraction is a common operation in organic chemistry lab, this video is very important. So let's start. So first of all, what is extraction? Extraction is the process of transferring one or more components from one phase to another. However, since in this video we are dealing with liquid-liquid extractions, you can understand that the phases we are talking about are two immiscible liquids. For example, let's say toluene and water. Liquid-liquid extraction in organic chemistry lab is performed using the separatory funnel, which is this tool you can see on your screen. This is the star of show today. So inside the separatory funnel, we will put the two immiscible liquids because it's inside this funnel that extraction occurs. So these two liquids can be, in our example, water and toluene, but in general we could refer to them as liquid A and liquid B. So now that we have done all the premises, let's explore how the extraction occurs inside the separatory funnel, and then let's see all the key equations to keep in mind. Picture this: liquid A containing a substance S. Then we place liquid A in contact with an immiscible liquid B inside the separatory funnel. What happens next? The substance will migrate from liquid A to liquid B across the interface between the two liquids. The migration continues until the equilibrium is reached. So we can write this equation that you can see here, where CSA is the concentration of the substance S in the liquid A, and CSB is the concentration of substance S in liquid B. As you can see, the ratio between these two concentrations equals K, which is the partition constant and depends solely on the temperature. So what happens? Our substance partially stays in liquids A and partially goes into liquids B according to this equation. From this equation is immediately clear that if K equals 1, the substance distributes evenly between the two liquids. So it will be challenging to take away this substance in just one of these liquids. However, this becomes much more easier when K is significantly different from 1. Now we can also rewrite the equation we have just seen using solubility, which means grams divided by the volume of the solvent. The equation becomes this one, where GSA and GSB are the grams of the substance in the liquid A and B, respectively. VA and VB are the volume of liquids A and B. So we have simply expressed the same equation in a different way. Now let's rearrange the equation in order to highlight the term GSB divided by GSA. As you can see from this equation, if I want to transfer my substance S into liquid B more than into liquid A, I need large volume of the liquid B for this to happen. So I have to increase the volume of my solvent B in order to increase the amount of my substance S into liquid B. However, from a practical standpoint, what is done in the laboratory is not so much about using large volumes of solvent B, because that's not cost effective. So what we do? We perform multiple extractions with small volumes of solvent B rather than a single extraction with the same overall volume of solvent B. What does this mean? It means that in my separatory funnel, I have my solvent A with my substance entirely within the solvent A. I add a small volume of solvent B where I want to transfer my substance, typically 1/3 of B compared to the volume of A, or sometimes even 1/5. And what will happen? My substance from volume A will partially transfer into solvent B, always following the constant K. Then, once the equilibrium is reached, I remove the solvent B from the separatory funnel and transfer it into a flask. So, in my separatory funnel, the solvent A will remain with the residual amount of substance S. After that, I add new pure solvent B, always 1/3 or 1/5 compared to the solvent A. The equilibrium is repeated, so more substance from the solvent A will go into the solvent B, again following the partition constant. And what I do next? Again, I will remove the solvent B from the separatory funnel and put it into the same flask as before. After that, I add more clean solvent B for the 3rd time. In fact, usually the extraction is repeated 3 times, but it depends on the cases. So we have now, again, more pure solvent of B, again 1/3 or 1/5 compared to the solvent A. And you can see that, again, substance S passes from solvent A to solvent B, following the partition constant. Then I will remove this volume of solvent B again and accumulate it in the same flask. And it's evident now that I have a large amount of my substance S into my flask with the solvent B, while I have depleted or almost exhausted the substance S in the solvent A. So I have achieved what I wanted, to transfer my substance to another solvent. And this is more convenient to do by repeating these extractions a certain number of times. So, as we have seen in the example, it's more practical to repeat the extraction n times rather than performing a single extraction with the same overall volume. So, if, for example, we use a total volume of 60 milliliters of solvent B, it's more convenient to perform 3 extractions of 20 milliliters each, rather than using the entire 60 milliliters for a single extraction. This is the concept you need to grasp. But let's understand mathematically why this happens. So why it's better to perform multiple extractions with a small amount of solvent than a single extraction with the same overall amount of solvent. Let's place this statement above as a reminder and delve into why this happens mathematically. So let's take the partition constant equation we wrote earlier using solubility. Now let's focus on the grams of substance S into the liquid A, and let's rewrite this amount as the initial amount of solute S inside the solvent A before the extraction, therefore before adding the solvent B, minus the amount of the solute S that has gone into the solvent B after the first extraction. So all we are doing is rewriting the current quantity of our substance S in the solvent A as the difference between the initial amount before the extraction and what has gone into liquid B after extraction. So we have this equation here. Now, if we rearrange the equation in order to obtain the amount of substance S in the liquid B, we get this equation here. This equation is the equation after the first extraction. So now what happens to this equation if we do a second extraction? The equation will be modified. So let's imagine to do the second extraction. So we remove our solvent B, as I have shown you before, and add the same volume of solvent B inside the separatory funnel. We add pure solvent B, while solvent A remains inside the separatory funnels and is the same volume, unchanged. So what are we doing? We are performing the second extraction. So our equation will be modified in this way if we consider the second extraction. Now it's immediately clear that for n extractions, I will have an equation of this type with n as exponent. Now, let's understand better these equations with a practical example. Imagine having 6 liters of ethyl acetate as our solvent B and needing to extract 200 grams of a product located within the aqueous phase with a volume of 2 liters. Obviously, in this example, water will be our solvent A. Let's also assume that K is 1. So let's pretend to perform a single extraction using all the 6 liters of ethyl acetate. So now we will take the equation with n equals 1 because we are doing just one extraction. Let's plug in all our data into the equation. So the entire 6 liters of ethyl acetate, the 200 grams of our solutes, and the 2 liters of water. What do we get? We find that from the first extraction we will gain 150 grams of our solute in the solvent B, so in ethyl acetate. So out of the 20 grams, only 150 grams will transfer to the solvent B, while the remaining 50 grams will stay in the aqueous phase. But what happens if we instead perform 3 extractions, each with 2 liters of ethyl acetate, until we reach the total 6 liters? To understand what we retrieve from the first extraction, we will again use the equation with n equal 1, but this time with the data for 2 liters of ethyl acetate. So from the first extraction, we retrieve only 100 grams of solute. But what's next? We need to perform a second extraction using again 2 liters of ethyl acetate. So to understand the amount we retrieve from the second extraction, we need to use the equation with n equal 2. This time we obtain 50 grams. But it's not over. We still have 2 liters of ethyl acetate for the last extraction, which is the third. So let's use the equation for n equals 3. We input our data in the equation, and as you can see, from the third extraction we get 25 grams of solute in our ethyl acetate. Now, if we add up all the grams we gained from the 3 extractions, we see that the total is 175. 175 grams is more than 150 grams obtained with a single extraction, even though we use the same total 6 liters of ethyl acetate. With this mathematical example, we now understand the statement we put on the top. The phrase is now clear. It's better to conduct multiple extractions with smaller amount of solvent rather than a single extraction with the same overall amount of solvent. Great, we have grasped the mathematical aspect of liquid-liquid extraction. Now, if you want to learn how to use this, the separatory funnel, you can go on my organic chemistry lab course that is available on my website operachem.com, and you can find the link in the description box. In this course I will explain to you not only how to use the separatory funnel, but also what to do after the extraction, because after extraction there are other operations to perform. So have a look if interested.